Let's welcome Dr. Kip Thorne.
In 1915, Albert Einstein gave us his general theory of relativity. This is actually a set of physical laws which say that space and time are warped by the matter and the energy that live in space-time. And they say that the warping of time produces the gravity that we feel here on Earth. Now, a half a century later, when I arrived at Princeton University as a graduate student, I was told that there might exist a warped side of our universe, by which I mean objects and phenomena made from warped space-time. And I shall describe several of them here today. I'll talk about the bulk, wormholes, black holes, singularities, time travel, and gravitational waves. Now, as a young man, I set a career goal for myself to explore the warped side of the universe using observations and theory. And so in this lecture, I will describe some of the things that we have learned in the last 56 years in this way. I'm having a little trouble that I don't have a monitor showing what I'm showing right here. If you can bring up the monitor, I would appreciate it. So I will describe what we've learned in the last 56 years, and by we, I mean myself, Stephen Hawking, Roger Penrose, Rainer Weiss, Lisa Randall, and many other of my colleagues. Now, I'm going to begin by talking about the bulk. I understand the bulk by telling you that space around the sun is warped in such a manner that the circumference around the sun is less than pi times the diameter. And we can visualize this by imagining that our universe is a surface, a three-dimensional surface called a brane or membrane that lives in a four-dimensional space called the bulk. But we want to remove two spatial dimensions so that we can visualize this on a screen. And so we have a universe that is a brane, that is a two-dimensional surface living in a three-dimensional bulk. Now, that surface is bent down in the vicinity of the sun, so the circumference of the sun is indeed a few kilometers less than pi times the diameter. Now, is the bulk actually real? In 1962, it seemed to me that obviously the bulk was real. Was not real, but in fact, in 1999, Lisa Randall told us that the bulk is real, to my great surprise. And I'm going to let Lisa Randall tell you about this in her lecture later on today. Now, if I take our universe between the solar system on one hand, on the left, and the galaxy Andromeda on the right, and I imagine bending it around so that in the bulk, so that the actual distance between our solar system and Andromeda is only a few kilometers, as seen across the bulk, then we may have a structure, which we call a wormhole, that reaches from our solar system up to down to Andromeda. And light can travel through that wormhole, like light traveling through a light pipe or an optical fiber, bringing us an image of what is on the other side of the wormhole. And this is the image of of what's on the other side of the wormhole, is computed for the movie Interstellar by my friends at the Double Negative Visual Effects House. And they even made for me a movie of what it looks like to travel through the wormhole. And in this movie then, we enter the wormhole very gradually with the Saturn off to the side, and light rays from Saturn get distorted. And we move on in through the wormhole and into the galaxy Andromeda. And here we are back in the galaxy Andromeda. Just in a matter of a few seconds, we've made the trip through the wormhole. Now, the unfortunate thing about wormholes is that they quite naturally want to pinch off and destroy themselves, collapse in upon themselves. And the only way to prevent that is to fill them with what I would call exotic material. By this I mean material that anti-gravitates, that repels the wormhole walls. And so the bottom line about wormholes is, first, that wormholes almost certainly do not occur naturally in our universe, unfortunately. And to exist, it's necessary to hold them, to create them, for a very advanced civilization to create the wormholes and to hold them open with exotic material. There is one exception to this, wormholes being artificial, and that is on very tiny scales of 10 to the minus 33 centimeters. There may well be a quantum foam of randomly fluctuating wormholes caused by the laws of quantum gravity, the new laws of physics that are obtained by combining general relativity with quantum theory, laws of physics that we don't understand at all well. And I will return to the laws of quantum gravity several times during this talk. Now, by contrast with wormholes, black holes actually do exist in our real universe. On the left, you see a black hole as sort of a failed wormhole coming down like a funnel to a point which is what we call a singularity. And if we want to know what the black hole looks like, as seen in our own universe, we can imagine having a star in the upper left and a camera in the lower right, and light ray travels from the star to the camera along that white path. Another light ray travels along the blue path around the other side of the black hole. And another light ray goes down around the black hole once to the camera. And so there are many, many light rays, can bring many, many images of the star to a camera. And when you then have millions of stars, you get a fantastic pattern in the sky that was computed for me by my friends at Double Negative in London. And it's just amazing to watch how that pattern changes as the camera pans, as the black hole moves across in front of the star field in the great distance. Now, it turns out that black holes in our universe are almost always surrounded by disks of hot gas called accretion disks. And they have jets of hot gas sticking out of them that then carry huge amounts of power out into the external universe. How do we know this? We know this because we see X-rays and light and radio waves all emitted by the jets and by the hot gas. And those X-rays, light, and radio waves have been analyzed to build the kind of picture that I've just shown to you. A remarkable thing is that in the wonderful, I now have a monitor I can see. It should go a little more easily. But the wonderful thing is that in the near future, we'll have an event horizon telescope that is going to enable us to make actual images of the huge black hole that is at the center of our Milky Way galaxy. This Event Horizon Telescope is actually a huge number of telescopes covering half of the Earth, where the data are all combined with each other interferometrically to produce very, very fine images of the tiny, tiny thing as seen from far away of the black hole and accretion disk at the center of our galaxy. What will that image look like? It may look like this. This is the image of the black hole Gargantua in the movie Interstellar. It's a black hole with a disk around itself, and the way in which this image comes about is quite simple. Light rays from the upper back left of the disk travel over the black hole and down to the camera. So the camera thinks that the light is coming from above the black hole, and so that produces the upper part of the image of the black hole, of the accretion disk. Then light rays from the bottom back face of the disk go down and up to the camera, producing the bottom part of the image. And light rays from the front of the disk come directly to the camera, producing the crossbar in the image. So a very simple explanation. This is called gravitational lensing of the accretion disk by the black hole's gravity. Now, let me turn next to Einstein's law of time warps. Einstein's law of time warp says that things like to live where they will age the most slowly, and gravity pulls them there. In other words, the Earth's mass warps time, and this time warp produces the gravity that holds you in your seats in this auditorium. And how much warping of time is required to produce the gravity we feel? It's a tiny amount, just 1 second in 100 years of slowing of time on the Earth compared to high altitude. This was actually measured for the first time with high accuracy in 1976, when NASA flew a rocket to very high altitude, 10,000 kilometers, and telemetered the ticking rate of an atomic clock in that rocket back to Earth, compared it with atomic clocks on the surface of the Earth. And to an accuracy of 1 part in 10,000, the accuracy of the experiment, the measurement agreed with the predictions of Einstein's relativity. Now, near a black hole, gravity is enormously stronger, and slowing of time is enormously greater. I have a black hole here as seen from the bulk. There's the black hole's horizon, the surface of the black hole. And if a rocket ship has descended to this location near the black hole, its time, the time measured in that rocket ship, is flowing 1/2 as fast as back here on Earth. If the rocket hovers right at the horizon, time as measured on the rocket is slowed to a stop compared to time here on Earth. Then what happens inside the black hole? What is slower than stopped time? Time flows in a direction you would have thought it was a space direction, down into the black hole, down into an object in the center of the black hole called a singularity, a place where the laws of general relativity fail and are replaced by the laws of quantum gravity, which we really would like to understand, but we do not understand as yet. What do the laws of physics say about backward time travel? Well, first they say that you cannot move backward against the forward flow of time. If you and your friend are standing here beside each other, the forward flow of time forces you to move in the same direction. It's impossible for me to move forward and you to move backward in time. Absolutely forbidden. On the other hand, general relativity by itself says that it's possible to travel out in space and come back, always moving forward in time locally, but come back before you started. Absolutely amazing. But on the other hand, the laws of quantum physics say that just at the moment when your trip is causing a time machine to be activated, the moment that this time machine that you're traveling along by going out and back is first activated, it is probably destroyed by a gigantic explosion created by circling huge amounts of what we call vacuum fluctuations of light traveling through this wormhole. It probably destroy it. We're not absolutely sure that it gets destroyed. Only the laws of quantum gravity know for sure. That's the conclusion of calculations and arguments that Stephen Hawking and I had with each other in the early 1990s. Let me finally turn to gravitational waves. Gravitational waves, according to Einstein, are warping of space that travels at the speed of light. And you can understand the kind of warping that this is by laying out a rectangular grid of particles floating freely out in interplanetary space. When the gravitational wave passes, it stretches and squeezes space, and the particles riding on space, which are our markers, enable you to see that stretching and squeezing. There's a stretching on one direction, squeezing the opposite direction, and the whole thing oscillates. So that's the nature of a gravitational wave, according to Einstein. In 1972, I began to develop, together with my colleagues and students, a vision for what we might do with gravitational waves if we could detect them. And you can understand the power of the vision, the power of gravitational waves for astronomy, by comparing the electromagnetic waves, that is light, X-rays, radio waves, that astronomers have used in the past, with gravitational waves. Electromagnetic waves are oscillations of the electromagnetic field that propagate through space as time passes. Gravitational waves are oscillations in the shape of space itself. Electromagnetic waves are incoherent superpositions of emission from individual particles, atoms, and molecules, whereas gravitational waves are coherent emissions by the bulk motion of large amounts of mass and energy. Electromagnetic waves are all too easily absorbed and scattered by dust and other matter between us and the source, but gravitational waves are never significantly absorbed or scattered, not even near the Big Bang, when the matter of the universe was very hot and very dense. This has major implications, these huge differences between these types of waves. First, gravitational waves, because they're made of warped space, they are the ideal tool for exploring the warped side of the universe. And second, gravitational waves are likely to bring our evolution in our understanding of the universe. Now, in 1972, the same year as I and my colleagues as theorists were developing a vision for gravitational astronomy, Ray Weiss, my friend at MIT, invented the kind of gravitational wave detector that would ultimately detect the waves. He said, let's hang 4 mirrors from overhead supports, 2 of them along each arm of an L-shaped vacuum system. The gravitational wave comes along and it pushes the mirrors on one leg of this L apart, pushes the mirrors on the other leg together, and that stretch and squeeze between the mirrors oscillates in a manner that tells us what's going on with the gravitational waves. And this, he said, we will monitor using laser light, using the technique of interferometry. I was so excited about this idea once I understood it deeply and saw that it really had a chance to succeed, that I convinced Caltech, my home institution, to build a research group led by Ronald Drever to work together with Ray Weiss's research group at MIT to build these kinds of gravitational wave detectors. In 1994, we brought in a director to lead our effort named Barry Barish, who talked here at the WE Summit, I think it was last year or the year before. And Barry, knowing how complex these detectors were and how hard it was going to be to make them, he expanded the team so it was much larger. That was necessary for success. And he expanded it to what is now about 1,200 scientists in 20 nations, including China. On the 14th of September in 2015, LIGO detected its first gravitational waves, our LIGO project, the first gravitational waves. They arrived and touched down on Earth initially at the tip of the Antarctic Peninsula. They traveled upward through Earth and emerged in Livingston, Louisiana, at our gravitational wave detector there, and then 7 milliseconds later at our gravitational wave detector in Hanford, Washington. By comparing the details of the oscillations, the so-called gravitational waveforms, with the predictions of supercomputer simulations, we deduced that the source was 2 black holes, each of them about 30 times heavier than the sun, that collided with each other 1.3 billion years ago. In a very distant galaxy, they orbited around and around each other. This is what they would have looked like to your eyes if you had been there. They collided and merged and emitted a huge burst of gravitational waves. So much energy that it was the same as you would get by annihilating 3 suns and turning all of their mass into gravitational waves. This is what that collision would have looked like as seen from the bulk. Each black hole is like a funnel, as I've shown you before, as seen from the bulk. The color coding shows the slowing of time near the black hole. And we slow this movie down to watch as the collision occurs. It's like a gigantic storm at sea in the ocean, and then an oscillation, and the gravitational waves go flying out. The power output, the energy per unit time, was 50 times higher than the total power out from all the stars in the universe put together. Now, LIGO has seen now 6 collisions of black holes, and we expect to see hundreds or thousands more in the next 10 years or so as our detectors are improved. LIGO, together with its partner gravity wave detector called Virgo in Italy, has seen 1 collision of neutron stars. Each neutron star is about 20 kilometers in diameter. It weighs 1.5 times what the sun weighs, and it has the density of 10 times an atomic nucleus. And the collision produced a gigantic fireball that emitted all forms of electromagnetic waves. About 25% of the world's astronomers went in and observed the aftermath of this, the electromagnetic waves, which came off a few hours and days after the gravitational waves. And from those observations, it was possible to deduce that a large fraction of the gold and the platinum in the universe was created by these kinds of neutron star collisions. What else might we see with gravitational waves? Well, we will watch black holes tear apart neutron stars. This is from a simulation. And you see fantastic visual appearance of this event of the black hole tearing a star apart. And we will observe the birth of the universe. Whatever came off of the Big Bang, birth of the universe, in terms of gravitational waves, is controlled by the laws of quantum gravity. They controlled what came off. But whatever it was is predicted to have been amplified enormously by what is called inflation, a very rapid expansion of the universe in its earliest moments. And so when we see these gravitational waves, primordial gravitational waves, we will get from them information about what came off the Big Bang and therefore about the laws of quantum gravity that govern the birth of the universe, and information about the inflation that amplified the waves. So in conclusion, it's 400 years since Galileo built his first optical telescope, pointed it at the sky, and discovered the 4 largest moons of Jupiter. It is 3 years now since LIGO turned on and saw its first gravitational waves from colliding black holes. When we look back 400 years and we see what enormous changes electromagnetic astronomy has brought to us in those 400 years, what a revolution there has been in our understanding of the universe, I invite you to speculate what will happen in the next 400 years with combined gravitational observations and electromagnetic observations. Thank you.